So let's look at another example of a summary statement using the new function family we are looking at today in this lesson of the form y equals 1 over x minus h. So we have this summary statement here. The function y equals 1 divided by x plus 2 has a vertical asymptote at x equals negative 2. So let's quickly recall what a vertical asymptote is. We learned today that a vertical asymptote is obviously a vertical line that the function will never cross. It'll get really, really close to it forever to any of the infinities, but it will never cross that value. So we are trying to see, is this true? Can we defend it using graphs, tables, and equations? So let's first look at this graph. Here we have this function y graphed. And as you can tell, the function kind of breaks. And the x value that the function sort of breaks at is negative 2. As you can see, above the y-axis, if I trace this, right, as we go closer and closer to negative 2, this function will continue to go up forever, but it looks like it won't cross. Same thing down here as we look down to negative infinity. If I keep going along, it's going to get really, really, really close to that negative 2 value, but never cross. So we're trying to show that there is a vertical asymptote, and usually it's a dashed or dotted line, the vertical asymptote at x equals negative 2. So this is just one justification. So this isn't as strong as 2 more. I'm going to go to Desmos right now so I can zoom out and further show you this asymptote and the function over time. Okay, so now I'm on the Desmos application, and here I want to show you when I zoom out what happens. So as I zoom out, keep looking at negative 2, the vertical asymptote, and notice right here as we go up forever and as we go down forever. I want you to pay attention to what happens. All right, as I zoom out more, you can't really tell, right? It looks like it does cross it, but it actually doesn't. You just can't tell. So maybe if I go in one direction and I choose a value really up high here, right? Let's see. Okay, so the x value of negative 1.972, that number is really, really close to 2, right? Sorry, negative 2. But as we go up, it'll never cross. See how it's going towards negative 2 slowly, but it will never cross. Now, if I go the other direction, all right, I'll start back at the middle. If I go down forever, right, it shouldn't cross that line. I'm just going to pick a random point. Okay, so negative 2.024 be the x value. That number is really, really close to negative 2, but we should never see it hit exactly negative 2. So we have negative 2.023 and then 2. So it's just going to keep getting closer and closer to negative 2 forever. But since it's an asymptote, it will never cross. Now let's look at another representation to justify this summary statement. Here's a table. So let's take a look at this table for f of x or y. Looking at the y values, hopefully you notice a trend here. So if we're starting at negative 5, we have negative 0.33333 repeating, right? Then we go to negative 1, which is more negative, negative 10 more negative, negative 100 more negative. And then we get an undefined value at negative 2. So that's interesting after looking at the graph representation, because on the graph we see just it never crosses negative 2, x equals negative 2 on the graph. On a table it shows up as undefined, meaning there is not a value there. So since there is no function value there, we can lead up to saying that there could be a hole or there could be an asymptote. But looking at the graph, that helped us realize that it wasn't just a hole, it was an entire asymptote. So we could pick numbers really, really, really close to negative 2, like negative 2.01, negative 1.99. If you recall when I was showing you the graph, we chose values really, really, really close, but it would never reach negative 2. It'll never cross it. So on a table, we can see the asymptote where it says undefined here. Now let's look at our last representation, which is the equation. So let's take a look and see where we could prove that there is an asymptote at x equals negative 2. Let's see what happens when we substitute in the input of -2. So it'll be 1 divided by, and then if we substitute x for -2, which we're saying is where the vertical asymptote is, let's see what happens. So I'll highlight to show that this was substituted right there. All right, so now we have 1 divided by -2 plus 2. If we simplify, we have 1 divided by -2 plus 2 is really 2 minus 2, which is 0. Okay, so now we're left with 1 divided by 0. We should know that we can never divide any number by 0. That's why we saw on the table the word undefined, right? That's what happens when we divide by 0. So it's like saying, how many times does 0 go into 1? It just doesn't make any sense. So in the equation, we see there being the vertical asymptote because when we substitute in -2 for x, we result in a 0 in the denominator, which results in an undefined number. All right, so that's using the equation. So if we go back to the original summary statement, we just used 3 different justifications to show that the function y equals 1 over x plus 2 has a vertical asymptote at x equals -2. We saw it on the graph, right, where the function approached positive infinity and negative infinity from both sides of the asymptote. We saw it in the table where there was an undefined value at -2. And then we saw it in the equation where when we substituted -2 in, we got 0 in the denominator, which we know we cannot do in math, right? We can't divide by 0. So it's just more powerful when you have 3 different representations to back up a statement. And in Algebra 2, this skill is going to prove to be very valuable for you as we get into more complicated function families.